Okay, so as promised, I'm going to go through these 5 problems, and I've got everything I need all set up. So I've got some graph paper, which is not required, but it makes things useful to make sure everything is lined up very nicely. I've got my questions, I've got a calculator, I've got my protractor, I've got something to write with, and then I also have something, a straight edge that's a little longer than what my protractor is, in case I have something that's quite long. Alright, so let's read the first problem. It says, a laser beam is aimed 15 degrees above the horizontal at a mirror that's 100 meters away. It reflects off the mirror and goes back for an additional 85 meters at 20 degrees above the horizontal until it hits its target. What is the resultant displacement? And whenever we see resultant displacement, especially a displacement, we have to calculate the magnitude and the direction, even if it doesn't say in parentheses magnitude and direction, of the beam to the target. So first thing, and when we did this in class, I insisted sketch the situation first and check with your teacher before continuing. So I'm going to sketch this on a different sheet of paper. So we know that we are starting from the horizontal. This says a laser beam is aimed 15 degrees above the horizontal. Horizontal is just the horizon. It's a horizontal line. In math, that would be our x-axis. 15 degrees above the horizontal means we're going that way from the horizontal. So we know our picture should go this way, and it'll go for 100 meters. The next part is the tricky part. So this, let me label this is 15 degrees and 100 meters. The next part can be a little confusing. We know we're supposed to go kind of backwards, so we know we're probably going to be going this direction. 85 meters, but 20 degrees above the horizontal can be confusing, because does that mean we jump down here and now we're at the horizontal down here? No. What we're going to do is we're going to go from the horizontal where we are, so we're measuring from this horizontal line, and we are going to measure up 20 degrees from there. And then our object is going to go 85 meters in that direction. Our resultant displacement is our straight line from start to finish. So if we start here and end here, we need a straight line from start to finish. So what we'll be looking for is the length of that line as well as what direction it's going in. So we're looking for some displacement and the direction. So that's what our picture will look like. And part of the reason why it's good to draw a sketch, especially if you're using a protractor and a piece of paper, is because then you can put the starting point in the right spot. So we started here and went a little to the right and a little bit more up. So it would be good to start our picture, when we draw it bigger, on this side of the graph, sheet, that we're not accidentally going off of our graph paper. Alright, so let's do that for real with the protractor. I'm going to do the protractor first this time, and then use that picture that I drew with the protractor to then show you how to do the calculations for it. So, pick a starting point. So I'm going to start over here. So you take your protractor and make sure you line it up, at least with, if you've got some notebook paper, then you can line it up with the, in this case, vertical lines. And if you have the graph paper, you can line it up both with the horizontal lines and the vertical lines. So the first one is going 15 degrees. So 15 degrees, this line here is 0 degrees, and then any increment this way is going to be counting up from 0. So 5 degrees, 10 degrees, 20, 30, 40. So 15 degrees is right here on my protractor. I like to make 2 dots, that way I can have a nice big, more lines to line up. And I'm going to first draw it with a nice sharp pencil. And the reason I'm using the sharp pencil, a nice mechanical pencil, is so that I can make this line plenty long. And then I go back along that line and I will measure it down. Oh, we forgot to make a scale. So first, we can't use 100 meters on this little piece of paper. But we can use a couple different things. We could use inches. We could probably, we could use 10 inches if we wanted. If we have a ruler instead, so we would use the protractor. And then we could use a ruler that has inches on it to go all the way to 10. It depends on what you want. The bigger your picture, the better. Because the bigger your picture is, the more accurate you can be with measuring and drawing your lines and measuring the angles and all sorts of things like that. Because I want to use this paper to show you the calculations, I'm going to keep it a little bit smaller so that I can write the calculations on the side when we go back and do the calculations. So in this case, and I'm going to write my scale up here. I'm going to use one centimeter is 10 meters. So every 1 centimeter is going to be 10 centimeters. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And the first one we go is 100 meters. So you have to make sure that for this step that you're very careful measuring. For the calculation way of doing this, you have to be very careful doing your calculations. If you're measuring, you have to be very careful with the measuring. So today when we were doing it in class, I noticed some students, especially for this first one, went from one edge of the protractor, the inside edge of the protractor, to the other, which would get you some error because you're adding a little bit extra to both sides. So make sure you're careful with measuring if you're using the protractor, and make sure you're careful with calculating if you use the calculation method. So 10 centimeters, and then from there, like we said in our little sketch, we're going to measure 20 degrees from the horizontal. So our ending point, and you might not end exactly on another line. If you just be very careful and very accurate. Don't line it up with a line just because it's convenient. Line it up with the end of your line like that. So this one goes here. And the other nice thing, like I said, with so many little grids, it makes it really easy to make sure everything is lined up, even if it's not exactly on a line. So now, 20 degrees, we're going 20 degrees this way, so 0 is over here, here's 20 degrees, so 20 degrees here, and then connect the lines. Again, I'm going to make it nice and big first, and then I'm going to trace back over it with the correct length. So this needs to be 8.5 centimeters because this is 85 meters. So this is 8.5 centimeters on our scale. And even though you're taking some time, being very careful and very accurate, this way does take less time. And this is even me saying this as a physics teacher, and I've worked these problems for however long. I can get through this problem super duper fast, being fairly accurate with this. With the protractor, and get a good estimate of what the answer should be a lot faster than doing the calculations. So our resultant displacement is here. Remember that resultant is the result of adding two vectors. So we added this vector. It has a magnitude, a length, and a direction. I'm going to label this 15 degrees. This one also has a magnitude and direction. So we have two vectors added together. So their result is this red line. And because this is for displacements, we call this a resultant displacement. There's a lot of different ways we can say a lot of different things in physics. So, now we measure. This looks like it's coming out to be 50. And the better you are at estimating, the better. So this looks like this is 5.8 centimeters, so that means with our scale this should be 58 meters. And then we also remember we still need the direction. A displacement is a vector, which means it has a magnitude and a direction. We know we've gone 58 meters, but 58 meters in which direction? So we place our protractor where we started, line it up. So this looks like, I'm going to make this line a little bigger so I can see it better with my protractor. So that looks like 72 degrees with this drawing. Okay. Now that we have a good idea of what our answer should be, let me show you how to do the calculations. Right now, this looks like it might be a 90-degree angle, and it might be. Maybe I no, it looks a little off. So if I've got this lined up like this, nah, it's almost a 90-degree angle, but it's not quite. I'm sure we could do some math and try to figure out what kind of angle that is, but don't rely on whether it looks like a 90-degree angle or not. This does not have to be a right triangle. There are some problems where we'll solve it with a protractor for momentum. There will be some cases where there is always going to be a right angle there. This is not it. This isn't it. So remember from when we solved this before, the first step was draw the picture. We have a picture. Very good step. Second step. Second step. Make right triangles. And there's going to be a couple ways to make the right triangles. Pretty much all of the time, the main way to draw the right triangles is to extend our vertical lines and our horizontal lines. So for our resultant displacement, we've got a right triangle kind of like that. For this first part of our displacement, we make a right triangle like this. And we know for sure these are right triangles, because that's by definition what they are. We know those are right triangles. There. Okay, so that's our second step. Make right triangles. And it doesn't have to be anything fancy. You're just going to draw a horizontal line, draw a vertical line, draw a horizontal line, draw a vertical line, horizontal, vertical. Our third step is to calculate components. So for this, I'm going to give these two vectors their own names. I'm going to call this one A and this one B. Those letters don't have any significance in physics. I'm just giving them a name so that I can write things out a little easier. It's like if your math teacher had a triangle and she called it R PQ or something like that. PQR. Right? It's just names. It's just letters. These letters are not like A for alphabet, B for beta, like V for vector. These are just names. Because I want to label this A X. So this is the length of this component is the length of A in our horizontal direction. Remember, X is for horizontal, Y is for vertical. So this one would be A Y, or the Y component of A in the vertical direction. And then B has the same thing. This is BY and BX. So, how do we calculate those components? Anytime we're calculating components, we're going to use sine and cosine, especially in physics, because most of the time we'll be given the angle and the hypotenuse of the right triangle. So anytime we have an angle and a hypotenuse, we use sine and cosine. Okay. Sine and cosine have the hypotenuse in their equation. Now, I'm going to use my This calculator is old, it's beat up, it is probably older than my son, because I had this in high school. So this is my high school calculator that I use to get me through high school physics. So you don't need a fancy TI calculator in order to do high school physics. And this is TI 30XA. And really what you need in a calculator for physics is sine, cosine, and tangent. Those are the most important buttons that you would need. This kind of calculator costs somewhere between $10 to $15. There are more expensive ones that look like this, but they're like $30, $35. You don't need one that fancy. All you need is one that has sine, cosine, tangent, and they should be in the range of $10 to $15. So I'm going to show you how to use it using this, even this kind of calculator. So, let's see, where do I want to write stuff? I'll calculate the components over here. So, A, is AX the adjacent side to our angle or the opposite side from our angle? And the way I like to think of it is when I was in high school, I liked to think that cosine is cozy. And the reason cosine is cozy is because we have these two sides kind of wrapping around our angle. So cosine is cozy, and then to get to the opposite side, just like if you have to get to the opposite side of town, or the opposite side of the school, or the opposite side of your room, you probably have to go through the middle of your room to get to the opposite side. So in this case, AY is going to be our opposite side, and we'll be using sine, and AX is the adjacent side, and we'll be using cosine to find it. Now, in math, you've seen sine and cosine as, let me start with cosine. Cosine of the angle equals the adjacent side divided by the hypotenuse. But right now, that's not in the most helpful form to help us solve this problem. We want the adjacent side equals something. So in order to get the adjacent side all by itself, we need to somehow move the hypotenuse to the other side. So in order to move the hypotenuse to the other side, we have to multiply, because right now the adjacent side is divided by the hypotenuse. So we multiply by the hypotenuse on. Alright, so this is going to be what we wind up having and we can flip the two sides. We have the adjacent side equals the hypotenuse times cosine of the angle. This is a really important version of this equation to keep around. I would recommend putting it somewhere important in your notes, because this is really useful, especially in physics, because most of the time we're not solving for a cosine of the angle, we're not solving for something else, we're solving for that adjacent side, the component, most of the time, and we have the hypotenuse. So for, and another way we would put this, so I'm going to write this using the letters we have. So AX, our adjacent side in this triangle, is A, which is the hypotenuse of this angle, times cosine of the angle, and this angle is 15. Well, I'm going to put just angle here. A, we know the length of A, that was the magnitude 100 meters. So A is 100 times cosine of 15. Now we have it in a form where we can just plug it into the calculator. These calculators are a little different than the TI-84s or the TI Inspires. These tend to be a little bit backwards. And the same thing with a cell phone calculator. So keep in mind that if you have a smartphone, you do have access to these things in your cell phone. You just need to turn off the rotate lock, and you have, I just changed it to degree radian mode, but you have sine, cosine, and tangent. I wonder if it'll, you have sine, cosine, and tangent in your calculator. But just like this calculator, it's going to be a little bit backwards. So rather than having 100 times cosine times 15, we have to go at it the other way. So we're going to have to do 15 cosine, so that gets the cosine of 15 times 100. So this is 96.59258. And like I said, I'm going to keep a lot of decimals until the very end. So it's best to keep a lot of decimals when you're working it at home until the very end. That way you don't have any rounding error. And I'm going to write this in my picture too. So 96.59. I'm going to write it a little shorter over here because it's a smaller picture. And then we need to do, I'm going to do, for AY, this is the opposite side, so we need to use sine in order to calculate it. Sine uses the opposite side and the hypotenuse. So if we're looking for the opposite side, we need to use, if we're looking for the opposite side and we have the hypotenuse, that tells us we need to use the sine trig function. And just like with cosine, this way of writing this equation is not very helpful. So we have to do the same thing. We're trying to solve for the opposite side, so we want to have the opposite side all by itself. So opposite side divided by hypotenuse. In order to cancel the hypotenuse on both sides, we multiply. So we get a very similar looking equation. We get the opposite side equals the hypotenuse times the sine of our angle. And again, this is another one that's very useful to have for physics, this version. Both are correct, both are valid. This is in a more useful format for us. Another thing to do, so notice how close in appearance these two equations are. They're not very different from each other. We have the hypotenuse times a trig function times an angle. And for this, we will have the same hypotenuse and the same angle when solving for these two sides. The only difference will be whether we press sine or cosine on our calculators. So it's always a good idea to go into your component calculations thinking about whether which side is going to be bigger than the other, and how it's going to compare to your hypotenuse. So we can see from this picture that the horizontal component of A should probably be pretty close to 100 meters. This is a very narrow triangle, so this should be pretty close to 100, and it is. And now when we calculate AY, this will probably be significantly smaller than 100. So let's see how that calculates. So AY equals A sine theta. Again, these are going to be very similar in appearance and how you press the buttons on your calculator. This is going to be 100 sine 15. So we have here, and again, this calculator has to work backwards, and probably also the same thing for your cell phone calculator. It has to work backwards. You have to put in 15 and then press the sine button and then multiply that times 100. So 15 sine times 100. So this is 25.8819. And that's what we estimated too. We estimated that it should be significantly less than 100. Okay, that's only part of the components for this one. In this case, there are two vectors that are at angles, so we need to calculate this one and this one, by and bx. But we've already arranged our equation the way we want, so I'm just going to write by equals b cosine theta. So b is 85 times cosine. Ooh, which angle though? Is it supposed to be cosine? Maybe I jumped ahead of myself. Let's go back. I don't know if it's supposed to be cosine or sine. Got this triangle, but we've got this angle. So where does that angle fit into our triangle? Is this 20 degrees? Is this 20 degrees? Is neither of them 20 degrees and we have to do some extra addition and subtraction or something along those lines? This comes back to geometry. So in geometry, when you have two parallel lines that are intersected by the same line, any angles that make a Z are the same angle. And this is called opposite interior angles, I believe. But in my mind, when I was in high school, I just knew that if it made a Z, it had the same angle. So, this line here, we had this horizontal line, and this is another horizontal line, and they're being cut by this line, so this angle is 20 degrees. Be careful when you're in physics, because sometimes physics teachers are tricky, and we don't give you the angle measured from the horizontal. We can give you an angle that's measured from the vertical. And that would change whether you use sine or cosine. So that's why I'm not using x and y in this equation. Sometimes math teachers will give you sine equals y over the hypotenuse, or cosine equals x over the hypotenuse. That's good for math because math always gives you the angle from the horizontal. But in physics, we don't have to always have the angle from the horizontal. And that can be tricky when we get to forces, because sometimes in forces, you'll be using a vertical angle and it'll switch. But what is always true is that the adjacent side is always related to cosine and the opposite side is always related to sine. So these are always true no matter how we're measuring our angle. This angle is measured from the horizontal, so the x component does match with cosine. The x component, the horizontal component, is our adjacent side of this triangle. So this is true. We have bx equals b cosine theta. So we have 85 cosine of 20 this time because this angle is 20. So that means, so 20 cosine 85. Oops, sorry, 20 cosine times 85. So we get 79.8739. Lots of decimals, and these all have a unit of meters because our hypotenuses have units of meters. And then again, for this component, so we have by equals b sine theta. B is 85, and we should have probably made an estimate with this as well. This is still a very small angle, and this should be closer to 85, and this one should be significantly smaller than 85. So again, working backwards for this calculator. So we have 20 sine times 85. This is 29.0717. If we also wanted to verify these and make sure we calculated it correctly, we can also measure, right? Because this was our scale drawing, we could also verify the components by measuring. So that looks like 2.8, which is good, which it would be good if we were estimating with the protractor and kind of getting a fairly close answer. But if we're calculating, we really want to just calculate it. Okay, so we've got all the components figured out. So what do we need to do next? The next step is going to be to calculate the components of the resultant. And this is just addition and subtraction. So we need to figure out how much we went horizontally overall, how much we went vertically overall. So we need to add this. And because we're going backwards this time, we need to subtract this to figure out this little piece. And then these are going in the same direction, so we add this to this. So these get added together. These are subtracted because they're going in opposite directions. Which should make sense, because if we're going in opposite directions, one thing should be positive and the other should be negative. So I'm going to call this Rx and Ry for resultant, the horizontal component of the resultant, and the vertical component of the resultant. So Rx equals I'm going to write it this way. Ax plus, oops, not plus, minus bx, because bx is negative. So this will be 96.59258. And again, I'm calculating now, so I'm going to have a lot of decimals. That way I keep all of my a lot of decimals until the very end, and then I'll narrow it down to just 2 or 3. Okay, now we subtract. 96.592. Can I go backwards on this calculator? Yes. 5.8 minus 79.8739. So this is 16.7186. Again, we're not quite done with this number yet, so I'm keeping a lot of decimals. 868. I'll keep one more. And I'm going to just put 16.71 over here. Our y component is ay plus a by. So ay is 25.8819. by is 29.0717. 25.8819 plus 29.0717. So this is 54.9536. Okay. Last step, pretty much. Last step for the magnitude. We still need to find the direction. Can you see why I've been insisting that you solve these with a protractor? Alright, so Pythagorean theorem. A squared plus b squared equals c squared. Okay, that's our last step for finding the magnitude. Just the magnitude, not the direction. But finding the direction is very simple once we've got all of this done. Okay, so I'm gonna use c equals the square root of a squared plus b squared. This is just the same Pythagorean theorem, but we've already solved for c rather than c squared. So in order to solve for c squared, we just take the square root of both sides. So, how you can do that on this kind of calculator, you can do it, but you won't be able to see it in the background. So I'm going to show y'all how to do that with this calculator. So let me write it down first. C is going to equal the square root of a squared, and a squared is going to be one of our sides, and b squared is going to be the other side. So we have rx and ry squared. So we have, this is going to be 16.781868 squared plus 54.9536 squared. And we can plug that all into the calculator all at once. Even one of these. Maybe I'll do 2 buttons for this one. But I'm going to do all of this at once. Okay, so let's see if we can plug this all into the calculator at once. So, what I want, in order to do this in really just one, like, I'm going to 2 presses of the button, what I want first is I want to make a parentheses here. So just to remind me. So I'm going to type parentheses, and if you notice, that opens a little parentheses over here. So, and the reason I'm showing you with this calculator as opposed to the really super easy TI calculator is to show you how you can do this with a simple calculator and actually do it well. You can also do it like this one plus this one and do it step by step as well, and that's fine too. Like when I was in high school, I would do this squared and then write down the number plus this squared and write down the number, and then I would add those together, and then I would take the square root. Because my family didn't have enough money for a fancy TI calculator, I had to wait until I got one in college for my math classes in college. So in high school, I just used this kind of calculator. Okay, so I opened up a parenthesis. That's this one. And now I'm going to type 16.71868 squared. So that's this number squared plus, I think it'll do it, 0.9536 squared equals. So that should be both of these things squared added together, and then I take the square root and I get 57.44 as my answer. And like I said, so this is our last step, so I'm not going to worry about too many decimals. You could keep it as just one. My general rule of thumb is like three digits, right? So 57.4, 7.44 if there was an effect, like 7.44, 0.444, whatever, meters. Not done yet. That's the majority of the work, but we're not done yet. That's how long this is. And notice how close that is. So when I'm making a test, what I'm going to do is I'm going to solve it. Like, I'm going to solve it both ways. I'm going to do a real quick sketch on my own to make sure I know, like, what the margin of error is. And then I'm going to calculate it to know exactly what it should be. And then, okay, so this one, like, it's supposed to be 57, but I got 58 when I drew it, so I know I need to add, like, a little bit on both sides, so in case it's a little bigger or a little smaller. So, in my opinion, and with all the numbers I was seeing today, it seemed like yeah, so somewhere between, like, for this one, it seemed like everybody was getting somewhere between 55 and 59. So I'm going to make sure, especially because I know other teachers don't necessarily teach this way, I am going to make sure and go through the test and make sure that if this is the answer, there is no both, like, you can choose 55 or 57 or 59 and 57. Like, anything within that range should be able to get you the correct answer, and there should be only one of those that's fairly close. And I'm going to try to make sure that there's, like, if this is the answer, I'm going to also make sure there's no, like, there might, well, 40 might be, because 40 is, like, 17 away, so there won't be a choice of, this will be an answer choice, and then there might be, yeah, so if you solve it using a protractor, and you get somewhere on this number, you know, like, oh, maybe I'll be a little up, a little down, but I'll make sure I go through and something that's really close, and you're like, ooh, I'm not sure, I'm going to try to make sure there are none of those around. Okay, so this is the magnitude calculated. Now we have to solve for the direction calculated. And usually the way I do it with my students is sine and cosine are for finding components, and then tangent is for finding the direction. You don't have to. Sine and cosine, pretty much you have to use those to find the components, but now that we have Rx, Ry, and R, essentially, you can use any of the trig functions to find the angle, but I find that students like having the regularity of sine and cosine are for the components, tangent is for the angle. But just like with sine and cosine, they're not in a form that we need. Same thing with tangent. So tangent of the angle equals the opposite side divided by the adjacent side. We are trying to solve for the angle. So the question is, how do we find the angle? How do we get rid of tangent? Sine, cosine, and tangent are trig functions. They're not just operations like add, subtract, multiply, divide. They're their own special thing. So they're functions. We can't just divide by tangent because we're not multiplying by tangent here. Tangent isn't a thing that we can multiply by. This is a function, and we put this into the function and something else comes out. In order to undo a function, we have to do the inverse function to both sides. So what we get is theta equals the inverse tangent of the opposite side divided by the adjacent side. This is another very useful version of your trig functions that you want to have in your notes somewhere. The question has come up, when do we use inverse functions? And that's only when you're trying to find the angle. If you're trying to find the angle, you have to get this function away, right? So for any of these, right, sine, cosine, tangent, if you're solving for the angle, then you have to undo the trig function that's next to it. So inverse functions are when you're solving for an angle. Now, the next question is, what's the opposite side this time, and what's the adjacent side? Well, that also really depends on what angle you want to use. So if we measured this one as 72. Okay. Where is that in this little triangle, though? And the reason I pause a lot of times is to make sure it allows you to think. So my pauses are not me thinking, they're to let you think. So make sure you're thinking. So if 72 is here, how does that relate to this triangle with Rx, Ry, and the hypotenuse? It goes back to this one again. This is, for physics, this is the most important bit of geometry other than knowing how to press the buttons for sine, cosine, and tangent. This is, in my opinion, the most important part of geometry, knowing that these z angles are the same, because we have more z's here, here. So this angle here is our is the angle that we measured before. So in this case, our opposite side is Ry, and the adjacent side is Rx. So we can write, I'm going to erase this line. We have the angle equals inverse tangent of Ry divided by Rx. So this is inverse tangent. Ry is, let's use the big number, Ry is 54.9536. Rx is 16.71868. So, inverse tangent, again, this is the same thing with this calculator. First we have to figure out this, and then we can press the button for inverse tangent, because calculators like this are backwards. So we have 54.9536 divided by 16.71868. So that's the answer for inside this bubble. And now we don't want to press tangent, we want to do inverse tangent. So second, and we can tell second is turned on because usually on a calculator like this, something like that pops up. On a cell phone calculator, when you press second, the buttons themselves change. So instead of being able to press tangent, it changes to inverse tangent, which is kind of cool. And we're in degree mode, so that's good. Second, tangent. So we get the answer of 73.1 degree. And this is, and we have to tell which way we measured from, so this is above the horizontal. Pretty close. So, what if you go wrong and you measure the wrong angle? You measure that angle instead. That's okay. That's a valid way to measure that angle. And our answer would be, if this is 90 degrees, and we've already gone 72 degrees, how much is left? Oops, I already cleared it. Oh well. 73.1 minus 90 backwards. So this would be an angle of 16.9 degrees, but since we're measuring it this way, this should be from the vertical. Both are okay. And I will, again, I'll make sure I'll go through the test, and probably I'll only have one of these available to pick. I'm going to try to go with the one from horizontal because that's pretty standard. So most of the time in physics we measure from the horizontal and go up. So I'm going to go through the test and make sure that only the one from the horizontal is available to pick. And if it's east-west, then it's the one from east or from west. So if you accidentally calculated this, and you're like, I don't see any of my choices, it's like 16.9 isn't even a choice. like, what do I do? Did I completely do it wrong? Not necessarily, right? Subtract 90, right? So if you have 16.9, do 90 minus 16.9, and hopefully you'll find an answer that's closer. So, that took a lot longer. Look at all that work. So we completely filled up the page for this one question. It took us like 10 minutes to do the picture, even going slowly, and with all my explanations, it took us another 50 minutes to do this. Now, it does not take you 50 minutes to do this because, one, there won't be one quite as complicated as this on the test. And two, you don't have to show every step slowly. Like, remember, I rearranged this equation to make it more appropriate for physics, and I explained how to do that. I showed you how to use the calculator, the small calculator, step by step. So even though it took us 50 minutes to do this, it took us 50 minutes to do this because I was stopping and explaining and writing every step, step by step. I did have some students work out both of these, number 1 and number 2, on today using this calculation method, and they got through both. So it is possible to get through both. It just depends on which method you prefer. Again, the method, especially for high school, it might just be easier to go through this year with the protractor. Make it easier on yourself. If you're thinking of doing college physics, or because you want to be an engineer or something similar, then knowing how to do this is really important, because for engineering, it is important to know how to be precise. This gives you a really good, close estimate, but for engineering and for physics, you do need to know how to do the calculations. Just keeping that in mind. It gets easier with practice, so if all of this scares you right now, don't let it scare you away from engineering or physics. This year is kind of crazy because, well, yeah.